In this video, we will see how to mathematically describe motion around a circle. Specifically, we will focus on the height of an object as it moves around a circle. We will create graphs that look like this one to describe that height over time. However, we are not limited to height. We can break down and analyze the horizontal motion around a circle in the exact same way, which is something that you could play around with after you watch this video. This video is for you if you're wondering why we would need a function like this, because motion around a circle seems really predictable even without any extra mathematical structure, or if maybe you're a student who is having to solve problems about this type of motion or about these types of graphs, and you feel like you have had to memorize a lot of information and you're wondering if there is a different approach. By the way, tools like the one you see me using now and will see throughout the video are linked in the description. Let's start by trying to answer initially that first question about why we need this. And one reason is that motion around a circle might not happen in isolation. So just describing motion around a circle, sure, that's predictable. But if I want to understand how that motion would combine with a general trend upwards and what specific things I might expect numerically out of that, I have to understand the circle first to be able to combine it. If I want to understand what happens if quantities are generally getting larger in magnitude while they travel around a circle and combine those together, you might get a graph like this. Both of these graphs that you've just seen could be graphs you've actually seen describing quantities in real life. We also could look at what happens if the motion is, for example, slowing down. And we can look at what happens if we combine different circles together. So this is a digital version of a toy you might have played with called the spirograph. It makes cool patterns. The other thing it we can do on this tool is actually graph essentially a height function, just like we've seen. And what you should observe immediately is that this height function is a lot less predictable and a lot more complicated, but it does come just from circles. And one important principle actually from much more complicated mathematics is that generally motion like this, even if it's not just a circle, even if it's unpredictable, we can describe by putting different circles together. And that has applications in sound and any kind of synthesis with those things. One quick note about what you need to already know to understand this video is on the screen right now. You do need to know right triangle trigonometry. So if you've ever heard the mnemonic SOHCAHTOA and that rings some bells, then you should be okay. You don't really need to know anything else. So let me do a very brief refresher of right triangle trigonometry. We need first a right triangle, and second, we need an angle. Once we have an angle, I'll call my angle theta, that completely determines the shape of this triangle. It does not determine the size, so this triangle could be large or small, but things like how those three sides, the hypotenuse, opposite, and adjacent that I just labeled, how they numerically relate to each other, maybe one side's twice as big as another, all of that is determined by the angle. And numerically, we describe that with ratios so that means division. And so there are more ratios than this, but the three basic ones, sine, cosine, and tangent, tell us how we can divide pretty much any combination of these sides in a way that we can calculate on a calculator and start to talk specifically numerically about these right triangles. So let's jump into a problem. Feels like a standard high school textbook problem. So again, for students doing these types of problems, I'm going to hopefully show you a different approach. And for the rest of us, it's just a good place to start. It's a nice visual. So we have a Ferris wheel, total height of 200 feet, rotates at a constant speed. One revolution takes 24 minutes. I did choose that number because it's easy to work with, but for reference, the London Eye takes 30, so this is not actually especially unrealistic for a big sightseeing kind of Ferris wheel. You're imagining that you're a passenger getting on the Ferris wheel at ground level, and we want to describe the passenger's height above the ground at any time during their ride. So height and time are the quantities we are trying to relate. Good place to start, almost always, is drawing a picture. So I'll label on the picture what I know about this problem. And then I want to show you a tool that I built that again is linked in the description that you can use to help you animate and visualize these sorts of situations. So I'm going to build this circle in this tool. I'm going to open up this top folder here. And I do not care horizontally where my circle is centered, so I will leave it at 0. But I do need the vertical center of my circle to be at 100 feet. The radius also is 100 feet. The period, P, is how long it takes to do one full rotation of my circle. That is 24. And I'll zoom so you can see this a little more clearly. This theta sub 0 is an angle. It's the starting angle. So if I move this around, my initial point will just be somewhere else. If you have a background in these types of problems, you might already know what I need to do, negative 90 degrees. There are other options. If you don't have a background in this, just slide it around until it looks how you want. In this case, we want, again, our passenger starting at the bottom. So now we've got this all set up. I can play time and watch the Ferris wheel move. Mathematical convention would be that a positive rotation is counterclockwise, so that's what I've chosen. But you'll see you can make it be clockwise, and since the Ferris wheel is starting at the bottom, it does not matter. I also can go ahead and create that height versus time graph. And I'll come back to this when I have made a function describing this relationship and check it and see if they match. So back to our slide. Let's start out with a table and just some specific numbers. It's very often a good place to start so you can intuitively understand what sorts of processes you might need. So I'm going to start at 0 minutes. I'm going to put that point visually on my circle. It's there at the bottom. I also know that after 24 minutes, we're back at that same point at the bottom of the Ferris wheel. The next most obvious time is if we split the ride in half. The passenger will be at the top, so that's after 12 minutes. If we kind of keep splitting in half, we have 6 minutes in the middle at 100 feet. With that second part in half, we're at 18 minutes, 100 feet. And then I think a natural place to go is to continue splitting in half, 3 minutes. What is the height of the passenger at that time? The most obvious guess is that you're halfway to 6 minutes, maybe you're halfway to 100 feet, that would be 50 feet. If we actually draw a line straight from 0 up to 100, you'll see that that purple point is not halfway there. It's less than halfway there. So we expect our final answer to be less than that 50 feet. And the other thing that drawing that showed us is that it's actually really not obvious what that height is. And so we will need to do a little bit more mathematics to figure it out. But I can take advantage of one thing, which is that there is a sense in which the passenger at this time is halfway to 6 minutes, and that sense is rotationally. The height's not halfway there, but the angle is, because that's how Ferris wheels work. They rotate. And this one rotates at a constant speed, so we've rotated 45 degrees from that red point at the bottom where we started. I have gotten rid of that red point just for some extra space to work. And at this moment, you might be thinking, I have an angle, I want a length. That's what right triangle trigonometry is built to do for me. So let's try and draw a right triangle using that 45-degree angle. So that right triangle will look like that. Really the only natural one you can draw using that 45-degree angle. And we can see the height right underneath that right triangle there. That's what I'm interested in. We know some things about the triangle. We know the radius of the circle is 100 feet, so the hypotenuse of the triangle is 100 feet. And we don't know that side there, but that side seems helpful, so I will call it x. And it's helpful because if I do 100 minus x, I'll find that part at the bottom that's left, the height. So I will go ahead and highlight all of these quantities that I'm trying to use. And now I'm all set up to do a trigonometry problem. So there it is, cosine 45 equals x over 100. I'm trying to isolate x, so let's do a little algebra. And then that's my relationship between height and x. Bring everything down, plug everything in, put it in a calculator, and I get 29.29. So I'll put that in my table. And just as a reminder, that's believable. We expected something less than 50, a good bit less than 50, and it looks plausible on our picture. Now would be a good time if you wanted to pause the video and try a few more of these. Pick some times that seem good to you and do the same process. Sometimes I might suggest are 2 minutes and 4 minutes. And you might want to stay between 0 and 6 minutes. That's the most illustrative quadrant of the circle to work in. But if you have a background in this, you also might want to check that this process works in other quadrants, because there are some weird things that happen with negatives. It does all work out if you don't have a background. That's a subject for another time. But again, if you've seen this sort of thing before, work it out for yourself how it works, even in different quadrants. So you can pause now and play around with that. Or we can move on, and our next step will be to do this with variables. So we've gotten our feet wet with numbers. We have explored and seen the process, and we're going to see if it works out with variables instead. We have a starting point, but now I've put that purple point at just an arbitrary place in the circle, which means my angle is just an arbitrary angle theta, again, a variable. But everything else is very similar. I still know that the radius is 100. I still don't know that side x, but I can still do 100 minus x to figure out my height. The other thing that's not so obvious is time. If we go back to our goal, it's to relate height and time. And time is not anywhere in this picture visually. And that's because time is related to angle. And because the Ferris wheel is rotating at a constant speed, the time is actually proportional to the angle. So we can set up a proportion for time and angle. So let's do that now. We know that one full rotation, 360 degrees, takes 24 minutes. So that's what we use to set up our proportion. Because theta is what's in the picture in the triangle, I need to isolate theta. So you see that happening now. And a little simplifying happening with the numbers. I get theta equals 15t. So now I'm ready to go back to the process that I did previously with numbers and do the trigonometry problem. It works out in a very similar way. So I can bring it down first and just substitute that 15t. Now I'm going to do the same algebra, isolate x, look back at my relationship between h and x, plug everything in, and put a box around it because what I have now is a relationship between height and time, which was my goal. So as I promised, we'll go back and check it over here. Let me turn back on that height function. I'm going to come down here at the bottom. I'm just going to type in what I just found. I'm going to use y and x because this plays a little nicer with desmos. So there it is. And I've made this green function show up right on top of the orange one, which means it matches, which means this visual approach and this proportional approach works. It describes this motion perfectly. Okay, so now let's look at another example, which off the bat is not actually a circle. What we're looking at here is temperature, the average high monthly temperature in Santiago, Chile for every month, starting in December, which makes December 0, which makes January 1, which is familiar to us. And what we see is that the scatter plot has a similar shape to the graphs we've been doing. And so we're curious if this circular motion logic works, even though temperature is not a literal circle the same way that a Ferris wheel is. And maybe we're even thinking that that would actually open this up to a whole new category of quantity and make this a lot more powerful if there actually are quantities that aren't literally circles but act like circles, that this would be useful to model. So let's dive in and see if it works as a way to model temperature. Looking back here to the slides. Here's that same data, and I'm going to draw a circle. I'm going to put the highest temperature at the top of the circle. I'm going to put the lowest temperature at the bottom of the circle. And then I'll just kind of visually space the other months around the circle for a sense of how this could work. I'm not going to go into too much detail. You can. When we get around to December, I have made that point red to remind us that's where we're starting. I could have labeled it m equals 12. That's how circles work, is that they repeat. So I could even keep going. I could add a little m equals 13 onto January, but this works for now. And next I'm going to look at these sizes. The actual numbers find the size of my circle. I see the radius is 13, which puts 73 right there at the middle, halfway between 60 and 86, which is our first good test of whether this might be a reasonable model. We see April and October are right on that middle line. And if we look at our table, the average high monthly temperature in April, month 4, is 75, which is pretty close to 73. And in October, month 10, actually is 73 exactly. So this is a good sign that this might be a reasonable model. Taking all of that down here with a little more space to work, let's add a point, an arbitrary point somewhere on our circle. I've got a variable x, and since x is going up from that 73 line, I know that my temperature is 73 plus x. Again, if you have some background in this, you can check for yourself that this works even in different quadrants. But for now, we'll stick in this quadrant. 73 plus x is how we're getting our temperature. We started at m equals 0, so there's our angle theta that we've turned from our starting point to this arbitrary purple point. And if we draw a triangle, right triangle, I need to take advantage of that vertical. One thing you might notice off the bat is that it doesn't perfectly match theta. So we need to break theta down into parts. The angle between December and January, if you split 360 degrees into 12 equal parts, will be 30 degrees. And I'll call the rest of it C. There we can see how the relationship works between theta and C, and then I've isolated C because C is the angle in the right triangle that I'll need for my trigonometry problem. So phi is what I need to actually use in the rest of this. Bringing that triangle down, labeling that hypotenuse, and just looking at where x actually shows up in this triangle. And then setting up a proportion with the angle and the time. So 360 degrees, 12 months. That's related to theta, the actual angle we rotate from December to the purple point. I need theta in my problem. I can simplify the numbers a little bit. All of that would tell me that theta equals 30m. And then I have a relationship between theta and c. C equals 30m minus 30. So now I'm good to go with my trigonometry problem because I have a relationship between C and M. So let's do that. So it ends up with cosine. If you do some other problems, it's not always cosine, by the way. That is what comes out of this, and this is where the visual approach is helpful, is that it just happens. You don't have to memorize, oh, in this situation I use sine or cosine. If you look at your picture, the sine and cosine just comes out of it. If I can bring this down and plug in my 30m minus 30 there, isolate x, look at my relationship between x and capital T temperature, plug everything in, and I get an equation relating temperature and the month. So let's go back at this point to our graph, plug it in, and see how well it works. We don't expect it to be perfect. And I remember that I do want to use y and x. Okay. We don't expect it to be perfect. We already know, for example, that April wasn't quite a perfect match, but it looks like it's pretty good. And so certainly as a starting point to model temperature, it seems like this circular behavior and these functions are a good model, which is useful because going back to something like this, many of us have seen graphs like this describing temperature in climate change. This idea of, yeah, temperature cycles, but it could also be trending upwards. And if I want to make predictions about how much it's going to trend upwards and then test actual data as it comes out, I really need specific numbers, and I need a graph like this that allows me to do that. So I want to leave you lastly with just a couple of practice problems, again linked in the comments, that you can do if you'd like. So we can play this motion. This is where you'll see, by the way, a small hint, you won't use cosine for this. But you have all the information, you know how big the circle is, you can see how quickly the motion is happening around the circle, and you should be able to set up and do a problem very similar and get an equation and type it in and see if you can map the orange curve. And once you've got that under your belt, you could try this one, which is like that graph we've seen a couple of times where you've got motion in a circle, also moving upwards. So think about how that interacts, where you're going to add that extra complication of moving upwards to the equation. That's it. Hopefully you've learned a new approach to circular motion and also how you might start to combine it in really limitless ways with other stuff and make lots of cool graphs. Thanks for watching.